welcome to this explainer. Right now, as you're listening to this, there is a literal microscopic battle happening inside your body. I want you to imagine just for a second that a single cell is not just some microscopic blob, but a complex, bustling city. It's got power plants, manufacturing hubs, waste management systems, and a strictly controlled border. But what actually happens to this thriving metropolis when it faces a catastrophic power failure? Well, today we are diving deep into the etiology and pathogenesis of cell injury. We're going to explore the exact biochemical changes that kick off when a cell gets starved of oxygen, and we'll trace that journey right down to the absolute point of no return. Let's get into it.
So here is the roadmap for our explainer today. 1. The setup. 2. The invaders. 3. The cascade. And 4. The point of no return.
Section 1. The setup. Adaptation versus injury.
Okay, we define cell injury incredibly broadly. It's essentially the effect of various stresses, what we call etiologic agents, that alter a cell's internal and external environment. Now, our cells are remarkably resilient. When they face an increased functional demand, they really try to adapt. They adjust their internal machinery just to handle the load. But there is a limit, right? When the stress becomes way too much, or maybe happens way too fast, it completely breaks their delicate internal balance, and that adaptation transitions into actual physical injury.
The absolutely crucial point here is understanding the difference between mild and severe stress. If the stress is mild to moderate, we're looking at reversible cell injury. Think of it kind of like a temporary power outage in our cellular city. Things slow down, maybe a few structures get slightly damaged, but if that stress is removed, the cell can completely recover and bounce right back. But if the stress is severe and persistent, well, we cross a fatal threshold into irreversible cell death. The damage becomes permanent and recovery is simply off the table.
Section 2. The invaders, causes of cellular stress.
So, what are the acquired causes of cell injury? We've got physical agents like extreme heat or trauma, chemical agents and poisons, think cyanide or arsenic, microbial agents like viruses and bacteria, plus, immunologic agents, nutritional imbalances, and even just the basic process of aging. But I really want to place a massive spotlight on the very first one, hypoxia and ischemia. Hypoxia is an oxygen deficiency, and ischemia is a loss of blood supply. Together, these two are by far the most common, most destructive culprits of cell injury. They are literally the ultimate power cut for our cellular city.
Section 3. The cascade. The biochemical ticking clock.
Right, so what actually goes down when that power gets cut? When oxygen is blocked by hypoxia or ischemia, this terrifying, highly choreographed biochemical cascade begins inside the cell. The ticking clock starts. We're going to walk through 4 crucial sequential failures that systematically dismantle the cell. It starts with the power grid failing, moves to toxic backup systems, leads to massive flooding, and ends with the physical breakdown of the cell's machinery.
Let's look at step 1. The power grid fails. Without oxygen, the cell loses its ability to generate ATP. ATP, adenosine triphosphate, is the literal energy currency of the cell. It is the electricity running our city. When ATP generation drops, everything grinds to a total halt. Essential membrane transport stops. Protein synthesis stops. Lipid metabolism done. The city is suddenly, violently thrown into the dark.
Desperate to keep the lights on, the cell switches to its backup generators, anaerobic glycolysis. Basically, it tries to generate energy without oxygen, but there's a really heavy price to pay here. This process creates a highly toxic byproduct, lactic acid. As that lactic acid builds up, we get intracellular lactic acidosis. The internal environment of the cell becomes highly acidic. The pH absolutely plummets, and this acid actually causes the nuclear chromatin, the cell's precious DNA blueprints, to physically clump together and become useless.
Okay, now we hit step 3, and this is where things get physically destructive. The cell has molecular pumps on its borders, most notably the sodium-potassium pump. And this pump requires a constant supply of ATP just to push sodium out of the cell. Without ATP, this pump completely fails. And the result? Sodium just rushes in and accumulates massively inside the cell. And a basic rule of biology, wherever sodium goes, water follows. The cell begins to gorge on water, leading to what we call hydropic swelling. The cellular city is literally flooding.
Finally, in step 4 of this cascade, the physical machinery itself breaks down. Ribosomes, which are the microscopic factories responsible for building proteins, begin to detach from the rough endoplasmic reticulum. With those factories dismantled and just floating away, protein synthesis drops to absolutely zero. So the city isn't just flooded and dark anymore. Its ability to repair or rebuild anything is totally gone.
Now here's the wild part. All of the damage we just covered, the swelling, the clumping DNA, the detached ribosomes, incredibly, up to this point, it's often still completely reversible if oxygen is restored. But that brings us to the most critical question of all. When exactly does a cell reach the point of no return? When does that reversible damage cross the line into an undeniable, permanent fatality?
Section 4. The point of no return. Irreversible cell death.
We have now arrived at that terrifying threshold. Once a cell crosses this line, it cannot be saved, not even if oxygen and blood flow are completely restored via reperfusion. So how do we know a cell has crossed it? Irreversible cell death is defined by catastrophic internal failures. Irreversible mitochondrial dysfunction means the power plants are permanently broken. Extensive plasma membrane damage means the city walls have completely collapsed. We also see massive calcium influx and severe nuclear changes. These are essentially the 4 horsemen of the cellular apocalypse, and these changes simply cannot be undone.
I really want to zero in on the massive calcium influx, because this is as fascinating as it is deadly. Normally, calcium is kept strictly locked out of the cell's main cytoplasm. But when those membranes tear, calcium just floods in, and this acts like an internal self-destruct sequence. It activates a swarm of deadly enzymes. You've got phospholipases that actively chew up the cell's membranes, proteases that shred the cell's structural cytoskeleton, and endonucleases that actively slice up the cell's DNA. The cell is literally digesting itself from the inside out.
And that brings us to the final, chilling collapse of the cell's command center, the nucleus. It happens in 3 distinct, horrific stages. First up is pycnosis. This is where the nucleus shrivels and condenses into a really tight, dark ink dot. Next is karyorrhexis, where that condensed nucleus shatters into tiny, fragmented pieces. And finally, karyolysis. This is where those fragments completely dissolve and fade away into nothingness. The blueprints of life are just gone.
Ultimately, it all comes back to this quote from our source material. Persistence of injury leads to the point of no return. It isn't just about the severity of the stress, it's the time. It is the relentless, persistent lack of oxygen that ultimately pushes that cell over the edge. Time is the deciding factor between a cell that bounces back and a cell that completely dissolves.
Which brings us to our final thought. As you sit here right now listening to this, billions of your cells are perfectly balancing this act. They're generating ATP, they're running their pumps, they're keeping the calcium out, and they're maintaining the city walls. I want to challenge you to really appreciate that constant, incredibly fragile biochemical balance. It's a balance that stands between a thriving cellular metropolis and the ticking clock of irreversible collapse, keeping you alive every single second of the day. Thanks so much for joining me to explore this truly incredible microscopic world. Keep learning, and I'll catch you on the next explainer.